While you're checking your fridge's temperature display and hoping the grid stays stable, your ancestors were storing a year's worth of food in a hole that never needed a single watt of electricity. When the power goes out, and it will, your refrigerator transforms from preservation machine into rot incubator within hours. The airtight seals that kept cold air in now trap heat and moisture, creating ideal conditions for bacteria that double every 20 minutes. By day 2, you're scraping black mold off what was supposed to be your emergency food supply. Meanwhile, 6 feet underground, the cache pit that fed the Mandan through brutal plains winters sits at a constant 50 to 55 degrees, untouched by the chaos above. The corn stored there last autumn is still dry, still edible, still waiting. This isn't primitive technology. This is engineering that never fails because it was never fighting physics in the first place. Your refrigerator is an active system waging constant war against the second law of thermodynamics. The compressor pumps heat from inside the insulated box to outside, moving thermal energy uphill against its natural gradient. This requires precision-sealed doors, refrigerant chemicals cycling through copper coils, and electrical power flowing without interruption. Every component depends on the grid, and the grid depends on power plants, fuel supply chains, and repair technicians with specialized parts. When that chain breaks at any link, the entire system collapses. The plastic interior lining that prevented condensation buildup now traps it. The foam insulation that kept external heat out now prevents internal heat from escaping. The sealed compartments that maintained separate climate zones become stagnant chambers. The interior reaches the bacterial danger zone, 40 to 140 degrees Fahrenheit, where microbial populations explode. Your food isn't just warming, it's being actively destroyed in an environment optimized for decay. The features that made the refrigerator efficient when powered make it catastrophic when it's not. The very design principles that enable modern food storage, airtight seals, non-porous surfaces, closed circulation systems, become liabilities the moment electricity stops flowing. This is the fragility of complexity. A machine with dozens of failure points, each dependent on industrial supply chains and technical expertise, pretending to be reliable infrastructure. You can't repair a failed compressor with tools from your garage. You can't replace refrigerant with materials from your backyard. The appliance is either fully functional or completely useless, with no middle ground. Across indigenous North America, from the Arctic coast to the southwestern deserts, engineers solved food preservation without external energy inputs. The solutions varied radically by climate and available materials, but the principle remained constant. Partner with the Earth's thermal stability instead of fighting it. The Inupiat and Yupik carved ice cellars into permafrost, shoring the walls with whalebone and driftwood to prevent collapse in shifting frozen soil. These vaults maintained true freezing temperatures, 0 to 10 degrees Fahrenheit, preserving seal oil and whale meat for years. The construction required understanding permafrost mechanics, where the ground stayed frozen year-round, how to prevent thaw cycles from destabilizing the structure, and how to position the entrance to minimize warm air infiltration during summer months. The Pacific Northwest Salish built pits on slopes with cedar bark drainage systems, solving the problem of how to keep food dry in rainforest conditions where groundwater pooled constantly. Their engineering focused on water management, channeling runoff away from storage chambers and selecting soil types that drained efficiently. The ancestral Puebloans of the Southwest constructed masonry-lined cists in dry cliff dwellings, using evaporative cooling principles to keep stored corn and beans viable through scorching desert summers. But the most sophisticated system, the one with the deepest ethnographic documentation, came from the northern plains. The Mandan and Hidatsa engineered bell-shaped storage pits that could hold a metric ton of corn for multiple years without a single moving part. These weren't accidents of trial and error. They were precision applications of geothermal physics, structural engineering, and material science, refined over generations of observation and iteration. Surface air temperature is chaotic. On the northern plains, summer days reach 100 degrees Fahrenheit. Winter nights plunge to 40 below zero. That's a 140-degree annual swing, with daily fluctuations adding another 30 to 50 degrees of volatility. Any storage system exposed to this turbulence would cook food in summer and freeze it solid in winter. The violence of these swings makes surface storage impossible without constant human intervention, bringing food inside during cold snaps, moving it to shade during heat waves, constantly monitoring and adjusting. But soil doesn't behave like air. It has thermal inertia, the property of resisting temperature change due to mass. A cubic meter of soil requires roughly 1,000 times more energy to heat than the same volume of air. This creates a damping effect as you descend. By 1 foot below the surface, the daily temperature cycle disappears entirely. The soil at that depth doesn't know whether it's noon or midnight. By 10 to 20 feet down, even the seasonal cycle flattens into a constant line. The Mandan and Hidatsa targeted 6 to 8 feet of depth. At this level, the soil maintains 50 to 55 degrees Fahrenheit year-round across the temperate northern hemisphere. This is the root cellar band, cool enough to slow the metabolic activity of stored tubers and the reproductive cycles of bacteria, but warm enough to prevent cellular damage from freezing. A potato frozen solid turns sweet and mushy when thawed. Its cell walls rupture and the starch converts to sugar. At this temperature range, it stays dormant and intact for months, its biochemistry suspended in a stable holding pattern. The cache pit doesn't create cold, it accesses a thermal layer the planet already maintains through sheer geological mass. The Earth acts as an infinite heat sink, absorbing minor surface fluctuations without shifting its deep temperature. This is passive refrigeration, no compressor, no coolant, no electricity. Just gravity and thermal mass doing what they've done for 4 billion years. The system is self-regulating. If surface temperatures spike in summer, the heat dissipates into the massive thermal reservoir of the surrounding soil before it can penetrate to storage depth. If surface temperatures plummet in winter, stored geothermal heat buffers the cold. The shape of the pit wasn't decorative. It was structural physics expressed in clay. The Hidatsa dug a narrow opening at the surface, roughly 2 feet in diameter, just wide enough for a person to squeeze through with a basket. This minimized the aperture exposed to outside air. Hot air rises and cold air sinks. A narrow neck prevented convective mixing that would bleed cool air from below while drawing warm air down. The opening functioned as a thermal plug, creating a stratified air column where the cooler, denser air stayed at the bottom and the warmer air remained near the surface opening. This natural stratification meant that even when the pit was opened for access, the temperature disturbance was minimal and temporary. Below the neck, the pit expanded into a bell shape, widening to 6 or 8 feet at the base. This created maximum storage volume, 30 to 40 bushels of corn, approximately 1,100 to 1,600 pounds, enough to provide 1.5 million calories. A family of 5 could survive 3 to 4 months on a single pit's contents. Villages with 10 or 20 pits could survive 2 failed harvests in succession. The bell shape also solved structural collapse. A cylindrical or square hole 6 feet deep would cave in under the weight of the soil overhead. The vertical walls couldn't support the lateral pressure of thousands of pounds of earth pressing inward. The curved shoulders of the bell distributed the overburden load down the walls, the same principle as a Gothic arch. The earth itself became the supporting structure, with each section of the curve transferring force to the adjacent section until the load reached the solid ground at the base. No timber shoring was required, which mattered on the treeless plains where wood was scarce and valuable, reserved for the construction of earth lodges and ceremonial structures. The walls were smoothed and packed hard using bone hose made from bison scapulae. Any loose crumb of dirt was a potential nucleation point for mold or an entry tunnel for insects. In some archaeological contexts, there's evidence of fire hardening, lighting a blaze inside the pit to bake the clay walls, essentially creating a low-grade ceramic vessel that sealed out groundwater infiltration. The heat drove moisture from the clay and partially vitrified the surface, creating a harder, less permeable barrier. This was precision engineering with Stone Age tools. The geometry wasn't guesswork. It was calculated in response to soil mechanics, thermal stratification, and compressive load distribution. Controlling temperature was only half the preservation equation. Humidity was the other half. Too dry and food desiccates into brittleness and nutrient loss. Too wet and mold blooms within days. The The challenge was creating a stable microatmosphere inside an earthen vault that was naturally damp, surrounded by soil containing residual groundwater and subject to seasonal moisture fluctuations. The Hidatsa solution was a composite lining system where each layer performed one specific function, and the layers together created a dynamic equilibrium. Layer 1. Dried grass and willow shoots bundled and laid against the floor and walls in a mat 4 to 6 inches thick. The hollow stems of prairie grasses, slough grass, bluestem, trapped air in their cores, creating an insulation barrier between the food mass and the cold earth. But the real brilliance was drainage. If condensation formed on the earthen walls behind the grass mat, it trickled down inside the gap between the earth and the grass, never touching the stored food. The grass functioned as a drainage plane. The grass also allowed microcirculation of air around the corn, preventing stagnant pockets where anaerobic bacteria could concentrate and begin producing the gases and enzymes that cause rot. Layer 2. Old hides, tipi covers, bullboat skins, any tanned leather past its prime use. These were pinned or weighted against the grass layer, forming a semi-permeable membrane. Leather breathes. It allows some moisture vapor to pass through while keeping loose dirt and grass debris from contaminating the food. The tanning process, whether brain tanned or smoke tanned, created a material that maintained flexibility in the cool, humid environment of the cache without degrading. It created a clean interior boundary, a container within the earth that could be removed, shaken clean, and reused season after season. Layer 3. Birch bark. This was the chemical shield. Paper birch contains betulin, a tritopene compound that is hydrophobic and naturally fungicidal. Water beads off birch bark. Fungal spores can't colonize it. Even buried for years, birch bark resists rot. Indigenous engineers across the northern forests used it as waterproof containers, canoes, baskets, and roofing material. In the cache, it functioned as the final barrier between stored grain and any residual moisture seeping through the hide layer. The bark could be shaped into containers or flat sheets. Layer 4. Wood ash, dusted on the floor or mixed near the opening. Campfire ash is a desiccant. It absorbs moisture from the air, lowering relative humidity in the bottom of the pit where cool air settles. It's also alkaline, with a pH high enough to disrupt bacterial cell membranes and prevent microbial colonization of the pit floor. And its microscopic particles are abrasive to insect exoskeletons. Weevils or ants attempting to breach the cache would be abraded and dehydrated by the ash layer, the same mechanism as diatomaceous earth used in modern pest control. Each material did one job perfectly. Stacked together, they created a dynamic equilibrium, breathable, not sealed. The cache regulated itself through material properties and natural physical processes, not mechanical intervention or human monitoring. The pit was only as effective as the food prepared for it. Storage began before the harvest even entered the ground. Corn kernels are living embryos. Each one contains a germ, the seed's embryonic plant, that respirates, releasing moisture and heat. If stored while still alive, the kernels would sprout in damp conditions or generate enough metabolic heat to trigger mold growth. The Hidatsa solution was parching, roasting the corn lightly over fire. The heat killed the germ, rendering the kernel biologically inert. A parched seed doesn't breathe, it doesn't sweat, it won't sprout. It's stable matter that will only degrade if external bacteria are introduced, and the cache environment was designed to exclude those. The parching process also drove off surface moisture without drying the endosperm completely, leaving enough residual moisture that the kernels remained palatable when cooked, but not enough to support microbial activity. Squash underwent a different treatment. The flesh was sliced into rings and sun-dried until it achieved a leathery texture. This process reduced water activity, the measure of available moisture for microbial use, to below 0.6. At that threshold, bacteria, yeast, and mold cannot function. Their cellular machinery requires free water to operate. Dried squash doesn't provide it. The cache merely maintained this dryness and protected the fats in the squash seeds from oxidative rancidity, which occurs when lipids are exposed to heat and oxygen. At 50 to 55 degrees in a low oxygen environment, those fats stayed stable. In wet years, some moisture infiltration was inevitable. When this happened, the cache transitioned into a different mode: controlled fermentation. The corn would sour. Far from being a failure, this was a recognized and valued outcome. Lactic acid bacteria, the same genus that ferments cabbage into sauerkraut, colonized the corn, producing acid that lowered the pH below 4.6. Botulism and most pathogenic bacteria cannot survive in that acidic environment. The resulting sour corn was safe, nutritious, and highly prized in Hidatsa cuisine. It had a tangy flavor and could be stored even longer than dry corn because the acidic environment actively prevented colonization by harmful organisms. This was empirical biochemistry. No lab equipment, no understanding of lactobacillus species or pH chemistry in modern terms. Just generational observation. This type of sourness is safe. That type of rot is deadly. The smell, the texture, the appearance. These sensory markers encoded complex chemical information. The knowledge was transmitted through apprenticeship, with elders teaching younger generation members how to distinguish safe fermentation from dangerous spoilage. A fully stocked cache pit was an infrastructure. It was a bank vault, a strategic reserve, and a trade commodity simultaneously. The Hidatsa and Mandan villages along the Missouri River became mercantile hubs because they mastered surplus production and preservation. Nomadic tribes, the Crow, the Cheyenne, the Assiniboine, followed the buffalo herds across the plains, living in portable teepees and eating fresh meat or dried pemmican. They had mobility but limited storage. The Hidatsa had the opposite: permanent earth lodges and underground vaults that could hold years of grain. This created complementary economies with different strengths and different vulnerabilities. This created a trade network. Nomadic warriors arrived in autumn with buffalo robes, parfleches of dried meat, and horses. They exchanged these for bushels of stored corn, concentrated calories that required no hunting, no processing, just transportation. The Hidatsa weren't selling fresh produce. They were selling stored energy, a commodity that retained value precisely because it could wait. A bushel of cached corn was worth more in February, when fresh food was scarce, than in September, when it was harvested. The cache enabled intertemporal arbitrage, allowing the Hidatsa to capture the value difference between seasons. The cache also enabled time freedom. A tribe that spent winter in desperate daily hunts for survival had no bandwidth for complex ceremonies, intricate art, or long oral storytelling traditions. A tribe with 3 months of food secured underground could allocate human attention to everything that makes culture rich. Complex ceremonies and elaborate oral histories required surplus, the freedom that comes when your next meal is guaranteed. Winter became a season of creation, not just survival. But this wealth was also a vulnerability. Below ground was a different reality than what appeared on the surface. Vast networks of bell-shaped vaults holding metric tons of grain. This invisible infrastructure was the foundation of plains economies, and it became the target during the Indian Wars. The United States Army realized they couldn't catch mobile warrior bands in open country, so they attacked the engineering instead. General John Sullivan's 1779 campaign against the Iroquois pioneered the tactic. Destroy not just standing crops, but the buried caches. Later Plains campaigns repeated this strategy, with cavalry units trained to recognize subtle surface signs marking cache locations. Burning a standing cornfield was insufficient because corn regrows the next season. Digging up and burning the buried stores broke the cycle. Without cached food, tribes couldn't survive the winter. They were forced to surrender or starve on reservations. The army understood the strategic calculus. Destroying one season's standing crop caused hardship. Destroying multiple years of cached reserves caused collapse. Cavalry units specifically searched for and destroyed cache pits. The military understood what many historians overlooked. The cache was the central pillar of indigenous national defense. It was a supply depot, economic engine, and strategic reserve. Invisible from the surface, camouflaged with sod lids and ash, but absolutely critical to survival. This wasn't collateral damage. It was deliberate economic warfare aimed at the infrastructure that made resistance possible. Modern survivalists stockpile generators to keep refrigerators running during grid failures. This is solving the wrong problem. A generator depends on gasoline, which depends on refineries, crude oil extraction, and global shipping networks. The failure point shifts from electrical grid to fuel supply chain, but dependence on external inputs remains. The cache endures because it's built on planetary constants that don't cease. Geothermal thermal mass at depth maintains stable temperature regardless of surface chaos, gravity-driven drainage channels condense without pumps, and material chemistry functions without human intervention. The Earth's temperature at 8 feet depth doesn't fluctuate with oil prices or supply chain disruptions. It's been 50 to 55 degrees for 10,000 years and will remain so for the next 10,000, barring geological catastrophe. Tapping into that stability requires knowledge: soil types, frost line depth, drainage patterns, and local materials with the right chemical properties. This knowledge can be transmitted person to person, generation to generation. It's encoded in practice and validated by results. This is anti-fragile engineering. The cache pit has no failure cascade because it has no dependencies beyond what the landscape provides. When the walls became sour, contaminated with persistent mold after several seasons, the pit was filled with trash, and a new one was dug 20 feet away. The repair process used the same tools as the original construction: digging sticks, bone hose, and local clay. The materials were renewable, the knowledge was local, and the labor was human-scaled. Compare that to a modern refrigerator. Average lifespan: 10 to 15 years by design. When the compressor fails, you need a technician with diagnostic equipment and replacement parts manufactured on another continent. When those aren't available, because of pandemic, economic collapse, or simple obsolescence, the appliance becomes a 400-pound paperweight. The cache also had capacity advantages that suburban fridges can't match. A standard kitchen refrigerator holds 20 to 30 cubic feet. A single Hidatsa cache pit held 300 to 500 cubic feet of usable storage, 10 to 15 times the volume, all passively cooled, all invisible to thieves or invaders. And the cache was decentralized. A village might have 50 pits scattered across the area, some inside earth lodges under the floor, others hidden in secret locations away from the settlement. If one was discovered and raided, 49 remained intact. Modern food systems are hyper-centralized. Grocery stores supplied by regional warehouses, supplied by national distribution centers. Cut the highway or the fuel supply, and the entire chain collapses simultaneously. We call ourselves advanced because we built machines that pump cold air into insulated boxes. We measure progress by the complexity of our compressors and the efficiency of our refrigerants. But the Mandan and Hidatsa didn't conquer cold. They didn't fight thermodynamics with machinery. They understood the Earth well enough to recognize it was already doing the work. They just needed to access it. The cache pit is uncomfortable knowledge because it reveals what we've traded. We traded resilience for convenience. We traded structural stability for mechanical dependency. Generational knowledge became planned obsolescence. The refrigerator requires an entire civilization behind it: power plants, copper mines, chemical factories, skilled technicians. The cache requires dirt, grass, bark, and the knowledge of where the frost line sits in your region. One system collapses if any link in a global supply chain breaks. The other system functions as long as you have a digging tool and soil beneath your feet. In a world where the grid is becoming less stable, where supply chains fracture under pressure, and where the complexity of our systems makes them increasingly brittle, the cache pit poses a question. What if advancement isn't building more elaborate machines? What if it's understanding the constants well enough that you don't need machines at all? What if the measure of sophistication is how little energy you need, not how much you can command? The ancestors didn't have universities or materials labs or thermodynamic equations written in mathematical notation, but they knew that 6 feet down, the Earth holds steady. They knew birch bark resists rot and wood ash kills insects. They knew dead seeds won't sprout and sour corn won't poison you if the fermentation is right. Your fridge will fail, the grid will fail, the supply chain will fail. These aren't pessimistic predictions, they're statistical certainties over long enough timescales. But the cache pit will still be holding steady at 50 to 55 degrees, preserving food in the dark, doing what it's done since the last ice age, partnering with the planet instead of trying to outthink it. That's not primitive. That's the kind of engineering that survives when everything else stops working. That's the kind of knowledge worth preserving when the lights go out.